day everyone, I am Nambatac Jr. and I will be going to discuss you these following topics. First, the Kirchhoff's law. Second, the mesh analysis. And the last one is the nodal analysis in AC circuits. So let's begin with Kirchhoff's law. Kirchhoff's circuit laws were first described in 1845 by a German physicist, Gustav Kirchhoff, and is widely used in electrical engineering. Kirchhoff's circuit law are two equalities that deal with the current and voltage in the lamp element model of electrical circuits. This generalized the work of George Ohm and preceded the work of James Clerk Maxwell. The first law, which is the Kirchhoff's current law or KCL, also called Kirchhoff's point rule, Kirchhoff's junction rule, or nodal rule. KCL states that the current entering in any junction is equal to the current leaving that junction. The second law, which is Kirchhoff's voltage law or KVL, is also called Kirchhoff's loop or mesh rule. KVL states that the sum of all voltages around a loop is equal to 0. In analyzing a complex circuit, one can either do nodal analysis using KCL or mesh analysis using KVL. Nodal analysis is a method of determining the voltage between points where elements on branches connect, or what we call nodes, in an electrical circuit in terms of the branch current. Mesh analysis is a method that is used to solve planar circuits for the currents at any place in electrical circuit. In this video, I will show you how to solve an AC circuit using nodal analysis. So this is our circuit. Find the node voltages using nodal analysis from the following circuit. See, we have two voltage source and one current source. We have two resistances, 3 ohms and 4 ohms, two inductances with inductive reactance of J2 ohms and J3 ohms. And we have capacitance with capacitive reactance of negative J2 ohms.
This branch impedance is Z1. Z1 is a complex number and it will be equal to 3 plus J2 ohm. Here this branch, the branch between this node 1 to ground terminal, I am denoting that branch impedance with Z2. Z2 will be equal to J3 ohm. Now see, between node 1 and node 2 I have this resistance. Let's say that branch impedance is Z3. Z3 will be equal to 4 ohm. Now see, between this node 2 to ground we have this capacitive reactance. Let's say that branch impedance is Z4. Here Z4 will be equal to minus J2. Okay. After that I will apply Kirchhoff's current law at this terminal and this terminal to find the node voltages. So at first I will apply Kirchhoff's current law at node 1 in phasor form. Apply Kirchhoff's current law at node 1 in phasor form. See, all the currents in the node number 1 will be unknown current because there is no current source connected in node number 1. So the current in this branch will be equal to V1 minus 12 phase angle 0 degree over Z1. The current in this branch will be V1 minus 6 phase angle 0 degree over J3 or Z2. and the current in this direction outgoing will be equal to V1 minus V2 over 4 ohm or Z3. So if I apply Kirchhoff current law here, I can write down V1 minus 12, phase angle will be 0 degree, and that branch impedance is Z1, plus V1 minus 6, phase angle 0 degree, that branch impedance will be Z2, plus V1 minus V2 over Z3. As there is no entering current, so right side will be 0. Now see, if I separate the coefficients, I will get 1 over Z1 plus 1 over Z2 plus 1 over Z3, that will get multiplied with V1, minus 1 over Z3 into V2 will be equal to 12, phase angle 0 degree, over Z1 plus 6, phase angle 0 degree with impedance Z2. Now if I put the value of Z1, Z2 and Z3 here, I will get, previously I showed you Z1 is equal to 3 plus J2, Z2 is equal to J3, and Z3 equal to 4 into V1 minus 1 over 4 V2 equal to 12, phase angle 0 degree, Z1 3 plus J2 plus Z2 is equal to J3 over 6, phase angle 0 degree. If you perform required calculation, you will get 0.48 minus J 0.49 V1 minus 0.25 V2. In the right side you will get 4.75 phase angle minus 54.25 degree, and this will be our equation number 1. After obtaining equation number 1, I will apply Kirchhoff's current law at node number 2 in phasor form. When applying nodal analysis, you will see from node 2, the current in this direction is unknown current, so this will be outgoing. The current in this direction will also be unknown current, so this will be outgoing, but the current in this direction is known current, and that is indicated by this current source. So in these two directions current will be unknown, and from this direction current will be entering. Okay, now see, if I apply Kirchhoff's current law at this node, I will get V2 minus V1 over Z3 plus V2 over Z4 equal to 3 phase angle 10 degree. So now I am applying Kirchhoff's current law at node 2 in phasor form. I will get V2 minus V1 over Z3 plus V2 over Z4 equal to 3 phase angle will be 10 degree. We know the value of Z3 and Z4. Let me separate the coefficients here. I will get minus 1 over Z3 into V1 plus 1 over Z3 plus 1 over Z4 V2 equal to 3 phase angle 10 degree. Now see, if I put the value of Z3 and Z4 here, I will get minus 1 over 4, phase angle will be V1, plus 1 over 4 plus 1 over minus J to V2 equal to 3 phase angle 10 degree. If we perform required mathematical calculation, we will get minus 0.25 V1 plus 0.25 plus J 0.5 V2 equal to 3, phase angle will be 10 degree. This will be our equation number 2. Here we have equation number 1. Here we have equation number 2. If I write down equation number 1 and equation number 2 in matrix form, I will get 0.48 minus J 0.49 minus 0.25 minus 0.25 plus J 0.5 V1 V2. In the right side we have 4.75, phase angle will be minus 54.25 degree. Here we will get 3 phase angle 10 degree. Now see, we can determine the determinants by using Kramer's rule. If I use Kramer's rule here, I will get the determinant of the coefficient matrix, that will be equal to 0.48 minus J 0.49 minus J 0 minus 0.25. Here I will get minus 0.25. Here I will get 0.25 plus J 0.5. The determinant of this matrix will be equal to 0.324 with phase angle equal to 21.23 degree. Okay. After calculating the value of determinant of the coefficient matrix, I can calculate the determinant of the coefficients of V1. In that case, I will replace this column with the values in this right side. In that case, the delta 1 will be equal to 4.75 phase angle minus 54.25, and here it will be 3 phase angle 10 degree, and in this column it will be minus 0.25. Here it will be 0.25 plus J 0.5. If I cross multiply this with this minus this with this, I will get 3.41. phase angle will be 9.36 degree. Okay. I can also calculate delta 2. Delta 2 will be the determinant of the coefficients of voltage V2. In that case, I will replace this column with the values in the right side. In that case, delta 2 will be equal to 0.48 minus J 0.49. Here it will be minus 0.25. Here it will be 4.75 phase angle minus 54.25 degree, and here it will be 3 phase angle 10 degree. Okay, if I cross multiply this with this minus this with this, I will get 3.21 phase angle minus 42 point, this will be 4 degree. Phase angle will be minus 42.4 degree. So our node voltage V1 will be the delta 1 over delta. This delta 1 is the determinant of the coefficients of V1. Here delta 1 is equal to 3.41 phase angle 9.36 degree, and delta is equal to 0.324 phase angle 21.23 degree. This will be equal to 10.52 phase angle 11.87 volt, and the voltage V2 will be equal to delta 2 over delta. Delta 2 is the determinant of the coefficients of V2. Here delta 2 is equal to 3.21 phase angle minus 42.4 degree, and delta is equal to 0.324 phase angle 21.23 degree. So V2 will be equal to 9.91 phase angle minus 63.63 volt. So these are the two node voltages for the given network. Okay, that's it. Thank you. In this video, I will show you an AC circuit example from the following circuit, or from the circuit shown in the following figure. Determine the current through AB path using mesh analysis. See, this is our given network. In the circuit, this is the AB path. We have to calculate the current through this AB path using mesh analysis. So for mesh analysis, at first we have to identify the total number of meshes in the network. It is evident that there are two meshes in the network. Let's say this is point C and this is point D. Let's say this is point E and this is point F. So you will see this F, E, C, D, F. Will form a mesh. Let's say that will be our mesh number 1. After that, this D, C, A, B, D, this will form another mesh. So D, C, A, B, D, that will be mesh 2. So at first we have to assign mesh currents in the meshes. So let's say in clockwise direction I am assigning the mesh currents. In mesh 1, mesh current will be I1. In mesh 2, mesh current will be I2 in clockwise direction. Now see, the current through this AB path will be the loop current in mesh 2. So I can write down the current I2 will be the current through the AB path. After assigning the loop currents, we will assign the polarities across the elements. The polarity of the elements depends on the direction of loop currents. The direction from which current will be entering will be the positive, and the direction from which current will be leaving will be negative. So this side will be positive according to current I2, this side will be negative. This side will be positive according to I2, and this side will be negative. The indication of polarity is similar to the indication of polarity in case of DC circuit analysis using mesh analysis. Okay, so don't get confused with that. After assigning the polarity, we will apply Kirchhoff's voltage law in each of the mesh in phasor form. You have to remember that the current I1 and I2 are phasor quantities. In some book you may see the current I1 and I2 has the bold case, or there could be a vector sign on top of I1 and I2. So here I will apply Kirchhoff's voltage law in mesh 1 and mesh 2 separately. If I apply Kirchhoff's voltage law in mesh 1 in phasor form, I will get plus 24 phase angle 0 degree minus 8I1 minus 10 I1 minus I2 minus J8 I1 minus I2 equal to 0. So if I simplify this, I will get 24 phase angle 0 degree minus 8I1 minus 10I1 plus 10I2 minus J8 into I1 plus J8 into I2 equal to 0. Or I can write it like this: minus 18 plus J8 I1 minus 10 plus J8 I2 will be equal to 24 phase angle 0 degree. Let's say this will be equation number 1. After that, we will apply Kirchhoff's voltage law in mesh 2. If I apply Kirchhoff's voltage law in mesh 2, I will get minus J8 I2 minus I1 minus 10 I2 minus I1 minus J4 I2 minus 4I2 minus J6 I2 equal to 0. If I simplify it, I will get J4 I2 minus 4 I2 minus J6 I2 minus J8 I2 plus J8 I1 minus 10 I2 plus 10 I1 equal to 0, which will be equal to 10 plus J8 I1 minus 14 plus J10 I2 equal to 0. Let's say this will be our equation number 2. Previously we deduced equation number 1 here. So if I write down equation 1 and equation 2 in matrix form, we can write it like this: 18 plus J8 minus 10 plus J8 10 plus J8 minus 14 plus J8. I1, I2. I1 and I2 are phasor quantities. In the right side I will get 24, 0. Okay. So this is the matrix form of equation 1 and equation 2. In this column we are taking the coefficients of current I1. In this column we are taking the coefficients of current I2. So using Cramer's rule we can calculate the current I1 and the current I2. For that, at first I have to calculate the determinant of the coefficients D. How do we calculate the determinant of coefficients? In one column we will take the coefficients of current I1. Let's say I will denote that with A1 and A2. In another column we will take the coefficients of I2. Let's say I will denote that with B1 and B2. After that we will cross multiply this one with this. That means A1 B2 minus A2 B1. So if I form the determinant of coefficients, in one column I will take the coefficients of current I1 and in another column I will take the coefficients of current I2. That will give the determinant of coefficients D. See, in this column I am taking the coefficients of I1. Let's say this is A1. Let's say this is A2. In this column I am taking the coefficients of I2. Let's say this is B1 and this is B2. Now see, if I cross multiply this one with this, take the minus of cross multiplication of this one with this, I will get the determinant of coefficient D equal to 189.53 with phase angle minus 135.86 degree. Okay, after that I will find the determinant of coefficients of I1. In that case I will replace the A1 and A2. I will replace this column with this one and this one. Let's say this will be C1 and this will be C2. In that case D1 will be equal to, in one column I will take C1 C2, in another column I will take B1 B2. After that I will cross multiply this one with this. That means B2 C1. I will take the minus of B1 C2. So if I take that, I will get a determinant of coefficients I1, which I will denote with D1. Here this is C1 and this is C2 and this is B1 and this is B2. So if I cross multiply this with this and take the minus of cross multiplication of this, I will get 387 with phase angle minus 150.26 degree. Okay, after that we will form the determinant of the coefficients of current I2. In that case we will replace this column with C1 and C2. That means D2 will be equal to determinant A1 A2. In this column we will take A1 and A2, and in this column we will replace B1 and B2 with C1 and C2. Again I will cross multiply this one with this. That will give us A1 C2. I will take the minus of A2 C1. A2 C1. So here if I take the determinant of coefficients of I2, that is D2, I will get this one will be A1, this one will be A2. In this column I will replace B1 B2 with C1 C2. Now if I cross multiply this with this, take the minus of cross multiplication of this with this, I will get 307.35 with phase angle minus 141.35 degree. Now I have the determinants of coefficient D, determinant of coefficients of I1 D1, determinant of coefficient of I2 D2. So here the current I1, the mesh current I1 will be equal to D1 over D. Here D1 is 387 phase angle minus 150.26 degree. D2, D is equal to 189.53 phase angle minus 135.86 degree. That will be equal to 2.04 with phase angle minus 14.4 degree ampere. Now see, we can also calculate the current I2. The mesh current I2 will be equal to D2 over D. Here D2 is equal to 307.35 with phase angle minus 141.35 degree, and D is equal to 189.53 with phase angle 135.86 degree minus 135.86. This will be equal to 1.62 with phase angle minus 5.49 degree ampere. And we know that the branch current in the circuit IAB is equal to the mesh current 2. So the current through AB path will be equal to 1.62 phase angle minus 5.49 degree ampere. What does that mean? This means that the current through AB path, the magnitude of current through AB path will be equal to 1.62 ampere, and that current IAB will be lagging at an angle of 5.49 degree to the applied voltage. Okay, that's it. Thank you.